Hi guys, and welcome back to my channel. In this video we'll be going over problem 4 from the Summer Chemistry Olympiad Bronze. So take a minute to read the problem, the description of the problem. I'm just going to skim it and sort of go through the important parts. Okay, so this says an old and open bottle of Barolo 2007 is wanted to determine its volume percent of alcohol. So basically we have some alcohol and we're trying to find the percent of ethanol that's actually in the alcoholic drink. For this analysis, a redox titration with associated two-step redox reaction is used. So we have a redox titration that's important to know. Okay, so let's look at the procedure and sort of decipher what's going on. We have some potassium permanganate, and permanganate is an oxidizer, right? MnO4 minus reduces really easily, especially in acid, to Mn2 plus. So it's an oxidizer, right? Okay, so we have a potassium permanganate in these conical flasks. Then we add some sulfuric acid. So basically that's the presence of acid, right? Okay, then we add the wine distillate. So we add the ethanol, right? Because wine, the alcohol is ethanol. We add the wine with the micropipette. The solution is then left to stand for 10 minutes, after which it can be assumed that all the ethanol has been converted to ethanoic acid. So basically this is telling us that we have some alcohol in the wine, and the permanganate is going to oxidize this, and it's going to form ethanoic acid. Does that make sense? Next, we fill a burette with ammonium ferrous sulfate as a titrator. The titration is performed on the oxidized ethanoic acid and permanganate solutions. So what is ferrous sulfate? Basically, what's important, as we can see if we look a little down, right, to the bottom of this page, we can see this second reaction. We see that Fe2 plus is basically oxidizing to form Fe3 plus, and at the same time, that's reducing the permanganate. So basically this is a reducing agent. Our ferrous sulfate is a reducing agent that's going to reduce things. It's going to reduce our permanganate, but yeah. So our Fe2 plus will reduce our leftover permanganate. That's the purpose of our ferrous sulfate. So let me go over what exactly I meant. So the first step, we're having our permanganate oxidize all the ethanol, right? So we're putting an excess of permanganate in. Then our second step, we're basically seeing how much leftover permanganate is there. By titrating it with this ferrous sulfate, that's going to cause the permanganate to reduce back into Mn2 plus. And what does that mean? That's going to cause a color change, and so we can see when the equivalence point is, we can see how much permanganate is left over. So if we can see how much permanganate is left over and we know how much we started with some excess of it, then we can figure out how much was actually used to oxidize the ethanol. If we can figure out how much was actually used to oxidize the ethanol, we can figure out how much ethanol there was in the first place. So that's the whole idea of this problem. So let's actually now go over how we can calculate this, right? Okay, so that was the whole idea of the description of the procedure. Now it says we perform a triple titration and the following results are obtained. So this titration is basically using ferrous sulfate to reduce the permanganate. That's the second equation is our actual titration. The first equation is our first step in the procedure where we just have an excess of permanganate and we're oxidizing all the ethanol, right? Okay. The titration, so we can see these volumes, and we usually perform a triple titration because it gives us enough leeway to sort of make sure that our results are correct, right? If we just perform one, we might not know exactly if that's correct. If we perform two, that's too little to sort of have a general, to know that both of them are in the same ballpark and correct. If we perform three and they're all sort of similar, we can take the average and sort of be confident that we did our titration correctly. That's why we sort of like triple titrations. And in the bottom, you can see that we're given our two reactions, but they're unbalanced. So we'll end up having to balance these so we can use some stoichiometric relations later on. So, okay, 4.1, why is it important to do at least a triple titration? I sort of briefly mentioned this, but just a good answer is that we can do basic sort of statistical tests, right? We can take the average, right? If there was just one, we might not be able to take an average of many trials. It's always better to have more trials than less. And if we take two, we don't really know the variation in our data, right? They could be like really, really off, or even if the average is sort of the average will be right in between them, but they could be really far apart, and that's not good. But with three, we sort of are able to find the variance and the mean, which is sort of good to be able to figure out, so we know that our results are correct. The next question is to balance the two redox titrations. So this is so we just need to balance them. How can we balance them? We can use half reactions, right? So the first one I'll do is Fe2 plus oxidizes to form Fe3 plus and releases an electron, right? That's our first thing. So the first equation I'm looking at is the actual titration, where we have ferrous sulfate reacting with permanganate. So this is our first half reaction. If we have our permanganate half reaction, we can do this too. Our permanganate reduces to Mn2+. Then we have to balance our oxygens, so we add 4H2O on the right side. This should be familiar from AP chemistry. Then we need to balance our hydrogen, so we add 8H+ to the left side. And finally, we need to balance our charge. So we have 7+ on the left side, 2+ on the right side. We need 5 electrons there. Okay, so then basically we want to cancel the electrons, so we have to multiply the first reaction by 5. And now we can add these two together, and we get 5 Fe2 plus MnO4 minus plus 8H plus goes to form 5 Fe3 plus Mn2 plus 4H2O. So that's our first balanced redox equation. The next equation we have is the oxidation of ethanol to ethanoic acid and the reduction of permanganate to Mn2 plus. So we have our half reaction for permanganate already, so we can use that. We just need to write the half reaction for ethanol to ethanoic acid, so let's do that. Our half reaction would look like CH3, CH2, OH is going to CH3, COOH, right? This should be our ethanol, and this should be our ethanoic acid on the right. Now, how do we balance this? First, again, we need to balance the oxygens. So we add H2O on the left side, right? Now we need to balance the hydrogens. So we can see that we have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens on the left side and 4 hydrogens on the right side. So we need 4H plus. Okay, and then we want to balance the charge, right? So we have no charge here, and we have +4 on the right side. So what do? We add 4 electrons on the left side. So now what do we have to do? We have to add the ethanol oxidation and the permanganate reduction together, and we need to cancel the electrons. So how can we do that? We need to multiply the permanganate oxidation by 4 and the ethanol oxidation by 5, so we can get the same 20 electrons in both expressions. So let me just do that really quick. Here I'm going to change this expression. I'm going to multiply it by 4. So we're going to have, this is going to be 32. This is going to be 4 MnO4. We're going to have 20 electrons. And then 4 Mn2 plus. And finally, 16 H2O, right? And now we're going to multiply the ethanol oxidation by 5. So we have 5 ethanols, 5 waters, 5 acids, 20 H plus, and 20 electrons. Now we just got to add these together, which this is a little bit tedious, but just hang with me, 5CH3CH2OH plus 4MnO4 minus plus 12H plus. So how do we get the 12H plus? We have 20 on the right side here, but we have 32 on the left side here, so they're sort of canceling out. Goes to form 11H2O plus 4Mn2 plus 5 acid. And the H2O, again, we're going to have this sort of cancellation. We have 16 on the right side here, 5 on the left side here, so we have this canceling out. But the net expression is this guy here. So this shouldn't have been like too difficult. It was more a little bit of tedious, but this is going to help us with the future questions where we need to look at the stoichiometric ratios, right? So I'll just box the two we actually need, or I'll highlight them. This guy, whoops. So we want this equation. That's our oxidation, that's our ferrous sulfate titration, and this equation. Okay, so now let's continue with the problem. Calculate the amount of MnO4 minus, the amount of permanganate that has reacted with ethanol, and find the equivalent amount of ethanol. Okay, so this is basically a little bit of, we got to look at the actual numbers now, right? So in the question, it told us that we had 0.02 molar MnO4 minus, and we had 20 milliliters of it. So what does this tell us? That means our initial amount of ethanol. So if I look at our initial amount of permanganate is equal to 0.02 molar times 20 milliliters, which gives us 0.4 millimoles, where millimoles is, so 0.4 times 10 to the negative 3 moles. So we have this initial amount of permanganate, right? We also know that it took, right, if we took the average, so if we look back here, and we look at the volume of the titrator used, the volume of the titrator used is the amount of Fe2+ that's used. So if we take the average of these three, we can see that on average we need 11.7 milliliters, right? So we can figure out how much Fe2+ was needed to titrate the excess permanganate. So let's look at that. N of Fe2+ till the endpoint, right, equals my 0.1 molar, that's what the concentration was of the ferrous sulfate, times my 11.7 milliliters, which gets us 1.17 millimoles again. So we have these two pieces of information. Now we want to look at our stoichiometric ratios, right? If I know the amount of Fe2+ till the endpoint, I should be able to know how much permanganate that reacted with. So let's look back at our equation. This tells us, right, if I look here, the first equation I wrote, that for every one permanganate that's being used up, 5 Fe2+ is being used up. So we have this 5-to-1 ratio between the ferrous sulfate, the Fe2+, and the permanganate. If I want to know the amount of permanganate used, given that this is the amount of Fe2+ that was used, the N of MnO4 minus used or reacted with the Fe2+, right, in my actual titration, is the 1.17, but we have to divide that by 5 because there's a 5-to-1 ratio, right, which is 0.234 millimoles. So now we started with 0.4 millimoles, and we only used up 0.234 millimoles of permanganate when we were titrating. So where did the other amount of permanganate go? That went towards oxidizing the ethanol, right? So the amount of permanganate to oxidize the ethanol is the 0.4 millimoles that we started with, and then we subtract off the amount that we know didn't react with the ethanol and instead reacted with the Fe2+, right? So if we subtract this, we get 0.166 millimoles. That's the amount of permanganate that reacted with the ethanol. And now it's saying find the equivalent amount of ethanol. So we want to look at the ratios and see what the amount of permanganate tells us about the amount of ethanol that reacted. Let's go back to our equation. We look at the second equation. We see that there's 5 ethanols. For every 5 ethanols, 4 permanganates are reacting. Or for every 4 permanganates reacting, 5 ethanols are reacting. So basically more ethanols are reacting than permanganates, and that's in a 5/4 ratio. So the amount of ethanol, CH3, CH2OH, that reacted, or the amount of ethanol in general, because all the ethanol will react, is equal to 0.166 millimoles. That's the amount of permanganate that reacted, but there's a 5/4 stoichiometric ratio. So we got to multiply by 5/4, and this gets us 0.2075 millimoles. So basically 0.2075 millimoles of ethanol is what's in our 100 microliter sample. Okay, the next question says calculate the content of ethanol in the tested wine expressed as volume percent. Then it tells us the density of ethanol. So we can see maybe we'll need density in order to convert from grams to volume. But the density of ethanol is 0.789. So we know that there's 0.2075 millimoles in our sample. So let's start from there. We have 0.2075 millimoles. Now if I want to convert this to moles, I just do, I don't need to convert this to moles actually, but if I wanted to convert this to moles, there's 1,000 millimoles, right, in 1 mole. So 1,000 millimoles over 1 mole. And I know the density, or I know the molar mass of ethanol. What is the molar mass of ethanol? You can calculate it yourself, but it's 46 grams per mole. So I can do 46 grams per 1 mole, right? So we divide by 1,000, we multiply by 46. This should get us the amount of grams, right? If you cancel out the units, you can see that we end with grams. But now I want it in volume percent, so let's instead convert this grams to volume, and that's where density comes in. So it tells us that it's 0.789 grams per milliliter. If I rewrite that to get 1 milliliter over 0.789 grams, and as you can see, I'm just using dimensional analysis. These units will cancel out and give us milliliters at the end of it. So if you go out with this calculation, and then I converted from milliliters to microliters because the milliliters was in scientific notation. So if we convert this to microliters, we get that this ends up with 12.1 microliters of ethanol. So basically, to make that more clear, what I did was in 1 milliliter, I did this. In 1 milliliter, we have 1,000 microliters. Because micro is 10 to the negative 6, milli is 10 to the negative 3. And if we plug this all in, we get 12.1 microliters of ethanol. And we know that our original sample, had 100 microliters of wine distillate. So our content of ethanol in the tested wine in volume percent is 12.1 microliters over 100 microliters times 100, which gets us 12.1%. So that's the answer we should get. And you can see this wasn't a super involved calculation. It was just a bunch of dimensional analysis to convert to units in volume percent. So why is it not necessary to use an indicator for this titration? What exactly was this titration? We had ferrous sulfate, just to remind us, reducing the permanganate to Mn2+. right? This was that's the backbone of my redox reaction. So what do we know about MnO4 minus and Mn2 plus? Mn2 plus is actually colorless. So these are some key facts to know, because I would recommend you know the colors of permanganate and Mn2 plus, because they come up a lot. This is really commonly used in redox titrations. Because these two are different colors, they naturally act as their own indicator. So MnO4 is a deep sort of purple color, whereas Mn2 plus has no color, it's colorless. So basically it acts as its own indicator, right? When the solution becomes colorless, I know that the MnO4 minus, the permanganate, has all reacted, and I know that basically we're at the end point. So when solution becomes colorless, I know we're at endpoint, right? So this is a really sort of, MnO4 minus is a really common oxidizing agent, and you should know the color because it acts as its own indicator, so it's really useful in that sense. Next question. Could the condition of the wine, open and old, have an effect on the titration results? Why or why not? If so, what impact, right? So let's think about this. Say the wine was open. This was the answer I thought about. If the wine was open and we have some ethanol, basically what that means is that air can come in and out of the wine, right? And as we all know, there's oxygen in the air, right? There's O2 in the air. And oxidants, right? When we talk about an oxidant, when we talk about an oxidizer, the original oxidizer, why we call it oxidizer is sort of because originally it was thought to it was being added oxygens, right? That's what it was like. That's what we thought it was. Oxygens are like being added. And a really common oxidizer is the oxygen in the air. So what we can think about, because oxygen is really electronegative, right? It really likes to hog electrons. So because of this, it likes to be reduced, it likes to gain electrons, and in that process, it's going to accept electrons from something else and oxidize something else. So basically, if oxygen in the air gets in the ethanol, oxygen can oxidize the ethanol. So basically, your ethanol is going to get oxidized to your ethanoic acid before you even do the titration. So what is this going to mean? This is going to mean that your ethanol concentration is less than what it should be, right? So ethanol concentration less than it should be. And what does that mean? That means that less permanganate is going to react with the ethanol, which means more permanganate, more MnO4 minus left over to react with the Fe2 plus, right? So we're going to have more permanganate left over to react with Fe2 plus, and that basically means that we're going to have higher volumes of our titrants being used. So we're going to have higher volumes of Fe2 plus used, and that's the effect it's going to have on our titration results. So just to walk through it again, if we have this open wine, air can go in and out of the wine. Oxygen is a really common oxidizer. Oxygen is electronegative. It likes to take electrons. It likes to hog electrons. That means it's taking electrons from something. That other thing is going to get oxidized, lose electrons. So ethanol will oxidize to ethanoic acid, basically because slowly, but because there is oxygen in the air. What does that mean? There's going to be less ethanol in the wine than it should be, right? Than there should be, because it got oxidized to ethanoic acid before we even did the titration and tried to measure stuff. And that means that if there's less ethanol, there's less permanganate going to be reacting with that ethanol. That means more permanganate is going to be left over to react with our titrant in our titration is going to be left over to react with the ferrous sulfate. And that means more ferrous sulfate is going to be used. Higher volumes of our Fe2+ will be used. And so our titration results are going to have, we're going to have higher milliliters, like we had 11.7 milliliters being used. We're going to have higher numbers than that if the wine was old and left to the environment. Okay, so that's the question I wanted to cover today. Hopefully this was useful. Thank you guys so much for watching, and I'll see you in the next one.